Well, the derivative of the denominator 1 over x is just negative 1 over x squared. One thing that I am able to do pretty much right away, as I can see here, I have quantities that are exactly the same, so common, you can say factors in a sense, dividing out to be 1. Moving on, what we have here now is a new fraction of which is 1 over 1 plus 1 over x. Plugging in infinity is quite nice now officially in that this ends up being 0. So 1 over 1, of course, just simply 1. If you remember towards the beginning of the problem, I was taking the natural log of both sides, of which led to us to be able to even do this in the first place. So natural log of y, again, the left side of the equation, equals this new value 1. The base, of course, on all natural logs is e, so we can rewrite this equation as an exponential. Here's e to the first power equals y. So quite brilliantly, what we are looking at actually is a limit um, of a function or an expression of which ends up resulting in e. In a sense, this is something you saw in pre-calc and algebra 2, but you didn't actually truly know what a limit was. So e, in fact, does have that kind of, I guess you can say, this expression to justify its origins. L'Hopital's rule can also be applied to one-sided limits, as demonstrated in the last two examples. So example 6. So we'll take a look here. As you can see, evaluate the limit as x approaches 0 from the right of sine of x to the x. Direct substitution yields 0 to the 0. So again, because we want the indeterminate form more specific to infinity over infinity or 0 over 0, we're going to have to do some similar things. Particularly, let's call this entire thing, including the limit, this expression, y. So if you take the natural log of both sides like we did in the last problem, well, natural log of y equals natural log of this entire quantity. Again, thanks to the continuity of natural log, we can move the natural log inside such that it's the limit of all of this, and we can use the power rule appropriately, moving the x out in front. A direct substitution, however, at this point, if you plug in 0, you get 0 times negative infinity, which is not what we're shooting for. So we kind of rewrite things. We write x such that it's 1 over x in the denominator. Instead of being multiplied by x, it's dividing by the reciprocal. Direct substitution now lends itself, if you were to plug in 0, to negative infinity over infinity. This is a form or version of the indeterminate form, I should say, that we are able to use, particularly in this case, such that L'Hopital's is applicable. So if we find the derivative of the numerator in the next step, derivative or ddx of natural log sine x, again by L'Hopital's, over ddx of 1 over x. The limit of as x approaches 0 from the right still, the numerator, the derivative of which is simply cosine over sine, while the denominator's derivative is negative 1 over x squared. We can rewrite the numerator as cotangent x, and that's still over negative 1 over x squared. And that is going to then be equal to, if I multiply by the reciprocal, negative x squared over tangent x. If we continue with this, and you can see here that I've got a little bit more analysis to be kind of identified here. 0 over 0 technically is still indeterminate. So yet again, by one more L'Hopital's approach or step, we can find the derivative of negative x squared to be negative 2x, the derivative of tangent to be secant squared x. Now plugging in 0, you get a limit of 0. So remember, the very beginning or early on, we were taking the natural log of both sides. So the natural log of y equals 0. Base e to the 0 power, which is just 1, equals y. So this particular function, sine of x to the x power, has a limit such that y equals 1, or a limit of 1. We're going to conclude with that. Example 7, I do want you to look at on your own, just to kind of see if you can make sense out of how the book performs some of the similar operations. This particular example is probably the hardest, of which you're using L'Hopital's rule in such a way where you're doing a subtraction of an indeterminate form. But take a look at it. It's a nice finishing touch to this particular section and semester.